Alright, so today we're going to be talking about the scientific method and kind of science in general. So in general, there are basically two kinds of science, or two approaches to science. There's origin science and operation science. Now, origin science, as the name would suggest, mostly deals with the origin of the universe. And so that is where you're going to get a lot of contention between, like Christian scientists and secular scientists, where we have the big division between creationism and evolution. Okay, so, and that really is the only area that it's looking at. It's just looking at how everything got started, where life came from, where the planets came from, and just that process. Now, on the other side of the fence, we have operation science. Operation science is what you would normally think of as the day-to-day work of a scientist, where they're doing experiments and testing things and looking for things. So this is where we're going to have geology, chemistry, physics, astronomy, biology, and a whole host of other different fields of science. Now, the big thing that happens in operation science is that they use a thing called the scientific method to test ideas. Now, the scientific method is a procedure that is gone through, and once we get into operation science, it's used by both Christian scientists that believe in creation and evolutionary scientists that are secular. It is a process for looking at things, and very simply, it can be very simply summed up into these 4 steps. You're going to look at stuff, think about it, make observations, look at the world around you, look at the way things are behaving. You're going to make a guess. Either this is why it happens that way, or if this happens, then that is going to happen. You're going to make a guess about something that's going to be based on your observations. You're going to figure out some way to test that guess. Within that, you're going to then look at your test results and decide if it's a good test or not a good test, all sorts of things like that. And then after you've tested it and you've looked at your results, then you're going to tell people. Now, more formally, we're going to go over here to the left. It starts with asking a question, okay? You're going to, again, observe the world. It's going to give you a question. There are all sorts of questions that we can come up with from looking at the world. And then you're going to do background research. See what other people have already found out about this. If you have a question and you can already find out the answer from a book or from another scientist or from another experiment, you don't need to do your own experiment. Because as amusing as the experiments are when we're, in school and small children, they're very lengthy, complicated, expensive processes when you're a professional scientist. So if you can find the answer, or if you can find something similar, you're going to want to get as much information as possible to either answer your question in the first place, or to help give you a framework of where you should go as you work on your own experiment. Then you're going to construct a hypothesis. This is your guess. But it's not just a guess that's coming out of your head from the middle of nowhere. It's going to be informed by all this background research that you do. So you've done this background research, you've gotten as much information as you can on the situation. You're taking it possibly a step farther, so you're just going to make a guess about that next step, taking into account everything that everyone who's come before you has done. Now, then you're going to test it with an experiment. You're going to come up with some experiment, whether it's an actual physical experiment where you're growing plants or dropping balls or doing that, or if it's like a social experiment where you're giving people a survey, something. You're going to somehow test it. And then you're going to analyze your results and draw a conclusion. Now in this, you can realize that your hypothesis is true, your hypothesis is false, or your hypothesis is partially true. You were kind of close, you were completely wrong, or you were completely right. Now, really, when we get to this point, I mean, it's nice to know if you're right or wrong, but really at this point, if you're going to like write a lab, you want to answer your question. You asked a question, so at this point you should answer your question. But here you also want to look at it to make sure that what you're doing, that your answer, the answer to your question, is not being influenced by some flaw that you had. So up here it says, do you have a personal bias? Did you have a poor test size, a poor experiment? And you're going to try the experiment again. You're going to look at your test, because if you're, trying to figure out why people, tend to get grumpy around a full moon, or, why small children have a lot of energy around a full moon, you can't really make any kind of reasonable conclusion based on 3 kids. Things like that. You want to make sure that you have a good test size. You want to make sure that we've talked about bias before, you want to make sure you're not clouding your judgment or making your experiment fit your expectations. You want to look at just what the data says. Okay, and if you find any of these, you're going to want to try your experiment again. Adjust your experiment, change your experiment, come up with a whole new experiment, and try it again. Now, most of the time, in professional science, where people are scientists, that is their job, most of the time their hypothesis is false. But, that doesn't really bother them, because if they know that something is not true, that takes one option off the table, So if you're looking at the world, you have 87, if your question is, why do plants grow better in the sun than in the dark, if you can eliminate the idea that it's because there's more air circulation when plants are out in the open, then it doesn't have anything to do with the air. There's a different factor that you're looking at. So even if your hypothesis is false, that's still useful scientific information because it narrows down the other choices. And so that's something that's still very valuable. So once you've looked at your conclusion, you're then going to report your results to, this one says, for peer review. You're going to take it back to other scientists and say, hey, this is the test, this was my question, this was my research, this was my guess, my test, these are my, this is my data. What do you think about it? And so they are then going to be very helpful in looking for this bias or any issues you have, because they are, different people. So if you're bringing in your own slant and you just really, really want to prove one thing, it might be easier for someone else to recognize that. Because a lot of the time, my personal belief is that a lot of the time when there's bias in scientific experimentation, it's often unconscious. It's not intentional. Or maybe that's just me hoping for the best, but I like to think that when scientists do put a bias on things, they're not doing it intentionally. They are just so set in their worldview that it's hard for them to recognize things that don't quite fit. So it's very useful to check with other people, and even people that, especially when it comes to bias, that don't necessarily have the same worldview as you, because if it is good solid science, it's going to be good solid science no matter who looks at it, even if they don't necessarily appreciate or like the results. The science will still be sound. Now, if they do find a problem with it, then they might challenge your results, so then you'll retest, develop, and conduct a new experiment. And that happens all the time. It happens all the time because of a poor test size or a poor experiment. You find out you have this great idea, you have this wonderful hypothesis, you go through, you look at it, and you say, well, that was a really good experiment, but it didn't really test the question I was asking. It tested this other aspect of the situation, which is good, and that's great data for that aspect, but it doesn't test what I'm looking at. So then you have to go and develop a new experiment. And again, these things happen all the time. Okay, so now as you're coming up with your hypothesis, there are things, or as you're developing your experiment, there are two different things that you really have to take into consideration, and that is your control and your variables. Okay, so your control is the current situation that you're looking at. For example, if you are, growing plants and you're trying to see, if fertilizer really makes a difference, your control would be, it would have no changes. It would be the standard against which you're measuring things. So you're going to have it in just plain soil. Okay, it's just going to be in plain soil. It's going to be water. Everything is going to be fine. Everything else is going to be just normal. You're just going to take the dirt out of your garden and just plant your seeds in that. Okay, so in addition to your control, you're also going to be looking at variables. And there are two kinds of variables. There are the dependent variables and independent variables. Dependent and independent variables are fairly easy to identify when you're looking at something that you are in complete control over, such as this experiment where we're seeing if fertilizer helps plants grow. So your independent variable in this case is independent of anything else. It is what is being tested. So that is going to be the thing that you change. So say, let's say this middle one is our control. It's just using dirt out of the garden. This one over here is using a mixture, and this one over here is using all fertilizer. And it's just an example. So the independent variable is the thing that you're testing. Now your dependent variable in this case would be how tall your plants are growing. It depends on the test that you're doing, especially at this point, is just that it's the thing that you're changing. The independent variable is what you're changing. The dependent variable is what you're measuring. Now in this situation with our plants, you then have to keep everything else constant. Okay, so all of your plants are going to get the same amount of water. They're all going to get the same amount of sunlight. They're all going to get the same amount of, air circulation, things like that. Okay, everything else has to be constant with your tests, and then you can really see if your independent variable is the cause of your dependent variable's change, if the fertilizer is really the thing that is making the plant grow. Okay, now, as we talked a bit before, when you're doing an experiment, when you're looking at things, ethics then become very important. And ethics are basically, it's a moral obligation to report the truth. You need, if you're the scientist, you need to say exactly what your data tells you. You can't change the numbers. You can't, say, well, this happened in my experiment that I tried to control all the variables for, but I didn't realize this happened in my experiment that I was trying to control all the variables for, but I didn't realize that this other thing was going to be a factor, and so therefore, clearly, that is the thing that, disproved my hypothesis. It wasn't my experiment, it was something else. This is where the peer reviews are very important, because you want to make sure that what you're saying is true, and other people can help you see if what you're doing is true or if you're skewing the data. You don't want to skew the data. You don't want to report like part of the data. You want to make sure that everything is there and you are presenting the information exactly as it is, with trying your hardest to take out your personal feelings, take out as much as possible your worldview. And those things are very hard, but that is definitely where you want to try and be. This is the area that a lot of, when we go back to, the origin science, this is where a lot of scientists get into difficulty on both sides of the creationist evolutionist debate, because whether anyone means to or not, they have a worldview. They go into a situation assuming that their experiment will fall on one side or the other, and that is then what we call begging the question, which is a kind of logical fallacy. Okay, and so when you beg the question, that's basically you go into an experiment and you just assume what the result is going to be, and so therefore you don't really take into account the data. You just say, my hypothesis was X, of course it's true, it doesn't matter what the data says, so therefore my conclusion is X. And that's definitely something that we don't want to get into, definitely something you want to be careful of in your everyday life, also not just in science. You want to make sure that when you're looking at things, you look at all the information and you're not just continuing to assume what you've always believed. There are lots of situations where you need to look at both sides of the argument before you can make a decision, and you need to be open to changing your mind about something.